So today we are going to speak about WKB, which is a very important technique named after three guys, Wigner, Kremers, and Brillouin, whose common feature is that they were not the guys that invented WKB. It was invented by 5 other people before, I think, and this is a perfect example of Arnold's law that says that no discovery is named after the person that actually discovered it. In fact, also Arnold's law was pointed out before Arnold. Yes?
WKB is not a method in quantum mechanics too?
No. This is one of the illusions that created by that is an artifact of the way physics is taught in undergraduate studies. The perturbation theory and WKB are considered as techniques that appears in quantum mechanics. Because in the course of quantum mechanics they teach you perturbation theory and they teach you WKB. But these are general techniques of what you call global analysis. That's right. So So again, what we want in WKB, what we want to do in WKB is to analyze equations of the form epsilon y double prime is equals to q of x y. Right? Now, before starting, I just want to point out something interesting, which is that every equation of the form every second order linear equation of this form, homogeneous linear equation of this form, may be written as y double prime is q of x times y. Right? So this is not a special case of something except of the epsilon, but every equation like that may be written that way.
How?
This is what I'm going to show you now. So, which is actually Schrödinger equation, up to playing with the parameters. So, Schrödinger equation is every second order equation. Why is that? If you want to see that, write y. Let's write y. Oh, this is not good. Let's write y as e to the power of, I don't want to use s, I don't want to use q, f. Right? So let's agree that y prime will be f prime e to the f, and y is g e to the f. So y prime is g prime e to the f plus g f prime e to the f, and y double prime will be g double prime e to the f plus 2g prime f prime e to the f. You see, one from taking the derivative of z and one from taking the derivative of z, right? Plus f double prime e to the f, f double prime g e to the f, plus g f prime squared e to the f. Okay? You see? So now, if we want to write this equation, okay, how this equation looks like. So we have that, this is y double prime. First of all, I can, y double prime is equals to z. So clearly, when writing it like that, the e to the f will cancel out. Okay? So we ended up with what? We ended up with g double prime plus 2g prime f prime plus g f double prime plus g f prime squared, right? This is y double prime plus a of x g prime plus a of x g f prime plus b of x g equals 0. Right? You agree with me?
Yes.
Good. Now, my goal is to get rid of the first derivative with respect to g. Right? So I want to get rid of this term and of that term. This will be true if 2g prime will be, 2f prime will be equal to minus a of x. You agree with me? Yeah. And therefore, f prime is minus 1/2 a, which means that f is minus 1/2. Okay, I don't need f. Which means that f double prime will be minus 1/2 of a prime. Right? So, first of all, by adopting this choice, of course you can calculate also f, but we are not going to need it. By adopting this choice, we got rid of this and that. Okay? And now what's left is g double prime plus g times f double prime, which is minus 1/2 a prime. This is that. Plus f prime squared, which is 1/4 a squared, plus a times f prime, which is minus 1/2 a squared, you see, plus b of x equals 0. So here it is, right? So every second order equation may be written that way by, so g will be y, and this is actually
But you
b
made an assumption that you can
minus 1/4 of a squared minus 1/2 of a prime, right? This will be q, and g will be y.
But you made an assumption that you can take 2f prime to be minus ax.
Now what's the problem?
It is an assumption. It's not all.
What does it mean? Just integrate a of x. Whatever a of x is, just integrate.
F was our choice. We put F. F was our choice. We put F to be there.
Sorry?
The only assumption is it's integrable,
Yes.
and you can take the derivative.
So essentially, we have seen here that every second order differential equation, homogeneous linear second order differential equation, is actually Schrödinger equation. So Schrödinger is not a special case, it's completely generic. Okay, so it's very useful to know that you can translate every equation like that to Schrödinger equation with a certain potential. And then you can analyze it the way we are going to show today. Okay, good. Having said that, let's proceed with the equation I've written here, which implies if you translate it to Schrödinger equation, this is like h bar squared, right? The time-independent Schrödinger equation. This is like h bar squared, and to make the analogy even better, we will define it as epsilon squared. Of course, it's just garbage, there is no different. Epsilon squared is just a parameter, but we want, for the sake of it is better like it. Okay? Of course, we can define square root of epsilon or epsilon squared. Okay. So how to analyze this? When again, what is the classical scenario in which we are required to analyze such an equation? This is true that the time-independent Schrödinger equation is of the form h bar squared over 2m d2 psi dx squared plus v of x psi, or let's call it phi, right? Plus v of x phi is e phi, right? With certain boundary conditions, which takes the form, right? We can write it as h bar squared over 2m phi double prime equals, sorry, I have a minus here, so I should multiply everything by a minus. So I have v of x minus e times phi, right? So the time-independent Schrödinger equation is exactly this equation, and the epsilon, small epsilon, means that this parameter is relatively small. The effective h bar or whatever is relatively small, meaning that we are approaching the classical limit. Because if h were h being 0, we have no quantum effects in the world. So h bar is going to 0 is like approaching the classical limit. So this is why it appears in the semi-classical analysis of the Schrödinger equation. Yes?
In the WKB theory, we will always assume that epsilon is small.
WKB theory is an expansion around for small epsilon, which is valid for small epsilon. Okay. So this was an introduction, and now what the technique is. Let's present the WKB technique. So the WKB technique, we assume that y is equals to the exponent of 1 over epsilon s naught plus s1 plus epsilon s2 plus epsilon squared s3, and so on and so forth, blah, blah, blah. That's y. This is how it looks like. Sum of Sn1 times epsilon to n minus 1 or something. Whatever. Okay, so let's see what's happened if we plug y here. Okay, what is y prime? Y prime is 1 over epsilon s naught prime plus s1 prime plus epsilon s2 prime, and so on and so forth, times e to the blah 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 times y. Okay, let's write it times y. You agree? What is y double prime? Okay, so first of all I have 1 over epsilon s naught prime plus s1 prime plus epsilon s2 prime blah 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 squared, right? This is one option. Plus, what else we have? We can take the derivative here. So 1 over epsilon s naught double prime plus s1 double prime plus s2 double prime plus blah blah blah. And all this is multiplied by y.
You forgot the epsilon and s2.
Epsilon. Yeah. Good. So that's all. This is everything. Now you know everything about WKB analysis. All the rest is consequences. Okay. So let's derive a few consequences. Okay, we plug this here, and we want to find out, and we want to write the answers in order by order in epsilon. Okay? So let's start. What will be the leading term in y double prime?
S not prime. נגזרת הראשונה של S0.
How the leading term scales with epsilon?
It's 1 over epsilon squared.
What?
1 over epsilon squared.
S not
Yes.
prime squared.
So we can write y double prime as 1 over epsilon squared times S naught prime squared. You see? Now what's the next term?
1 over epsilon.
1 over epsilon.
I have 1 over epsilon times what?
S
S
not
not
double
prime.
prime
S naught double prime
plus
plus
S not prime multiplied by 2 with every
plus. What will be the next term? The next term is order 1,
yes.
right? And
Yes.
this will be more what?
S1 prime squared
Plus
plus
S1 double
S1
What?
plus S1 double prime plus S0 prime S2 prime.
Plus epsilon times something and so on and so forth. You see? Any questions? Good. Now we plug it here. So to the now note that we have an epsilon squared here, right? So the epsilon squared cancels this, right? So to the first order or the zeroth order WKB is S naught prime squared equals Q of X. You see? That's the zeroth order. And the answer is, first of all, I should take the square root of Q and then integrate. So S naught is the integral up to X of plus minus, of course, square root of Q of T dt.
Up until constant.
What?
Up until constant.
Yes, we throw all the constants because the constants are not important. Good. First order. Now I have to collect things that are order epsilon, right? Because I have this was order epsilon to the 0. This will be order epsilon. Now on the right hand side, do we have something order epsilon? No. On the left hand side, however, we have this. So we have S naught double prime plus 2S naught prime S1 prime equals to 0. What's the solution here?
You know that's Q tag and that's Q double Q prime.
So we can write, okay, we know S naught. So now we have to say that S1 prime is minus S naught double prime, S naught double prime divided by 2 S naught prime. See, algebra. And this implies, and this is minus 1/2 of the logarithm of S naught prime. Prime. You agree with me? So this is S naught double prime divided by S naught prime. Okay? So S1 prime is minus half something else prime. So S1 without prime is minus 1/2 ln of S naught prime. But what is S naught prime?
plus minus.
S naught prime is the plus minus the square root of Q, right? So this is minus 1/2 the logarithm of the square root of Q of X, and logarithm of the square root of half the logarithm.
Yeah.
So this is minus 1/4 ln Q of X. Right? Now you are asking why I'm not taking the plus and the minus.
Yes.
I will address this in 2 seconds. Right? So, importantly, I'm going to write S1 is minus 1/4 times the logarithm of Q of X.
What to do if Qx is negative?
What?
What to do if Qx is negative or
That's
0?
the same question, right?
And
Okay.
what if it's 0, it is undefined?
Okay, good question. Everything. But yesterday I said I'm not going to address the point where A of X is crossing 0. So this is the same problem, and now we are going to address it. Okay? And if I want to calculate S2, what I should do? What should I do?
Take over epsilon.
I should
squared.
take this.
Yes.
I know S1, I know S0, and I have to solve for S2. Right? So I'm writing S2 prime is equals to minus S1 double prime over 2S naught prime minus S1 prime over 2S naught prime, and this is whatever it is. Right? Of course, it becomes more and more complicated for higher and higher orders, and of course, we usually use only the first two terms. Okay? Good. What? So fine. So you see what the trick is. Okay? So for example, let's take a very interesting example. Which is epsilon squared y double prime is minus plus, sorry, is xy. What is that? Area. This is area up to the epsilon squared, right? And the answer is now, what is q? Is x. So s naught is the integral up to x of square root of t dt plus minus, which is plus minus 2/3 x to the 3/2. And S1 is what? Is minus 1/4 ln x. So plugging that into our expression for y,
This is exactly what we got when we used dominant balance.
No.
not one dominant balance, but local analysis.
Local
Oh,
analysis.
wait. So plugging it here, what I will get is e to the what? So what is y? Y is asymptotically equal to what? To e to the plus minus 1 over epsilon 2/3 x to the 3/2, right? Plus minus 1/4 ln x, but e to the ln x is x, right? So we have x to the minus or divided by x to the 1/4.
Why are you saying that y is asymptotic to this?
What?
I mean, everything we've done until now, it's global. When you're saying to something it's asymptotic, it's local. You have to specify
No.
the point.
It's asymptotic in the limit epsilon goes to 0.
Okay.
This is asymptotic in the limit at, okay. I stopped, during the course, I stopped writing this mufraut of writing every time at epsilon goes to 0. Yes? Now there is your very smart comment that we have already discovered when we did local analysis that y from the local analysis we have already discovered that y is asymptotic to e to the plus minus 2/3 x to the 3/2 divided by x to the 1/4 at x goes to infinity. Right? You see?
Yeah.
Now, first of all, I just want a side remark. You remember that when we did local analysis, we have a lot of questions about when we are able to write asymptotically equal to when we calculated only the exponent, right? And we decided that it will be true when the extra correction will go to 0 as epsilon goes to 0. So now it is, you are, I mean, you see immediately that this is what happened. Because by construction, this is what happened. Okay? Second, okay, so how come that we get the same answer? First of all, it's not exactly the same answer. Why? Because I have epsilon there and I don't have epsilon here.
Yeah, but epsilon goes to 0 and you have 1 over epsilon, which is equivalent
okay.
to x goes to infinity.
Great. So in order to make your argument more precise, let's consider the... you don't have red. Okay. Let's consider the area equation of the for epsilon y double prime is xy, right? This area equation. Okay? Now I want to absorb the epsilon. Okay? How do I do that? I will define z as gamma times x. Okay? So ddx is ddz. Do I want it? I have to remind myself if it's gamma or 1 over gamma. Yeah, x over gamma. So I have a gamma f. Okay? And which implies that the equation is epsilon over gamma squared times y double prime, where now the prime is with respect to z, right, is equals to x, which is gamma z, times y. All in all, we have y double prime equals to gamma cubed over epsilon times zy. Okay? So if we will choose gamma cubed equals to epsilon,
you get the opposite equation. You get y double prime equal epsilon squared zy.
no, if gamma, sorry, this is epsilon squared, sorry. So if gamma cubed is equal to epsilon squared, meaning that gamma is equals to epsilon to the power of 2/3, this choice will give me y double prime is zy.
Exactly.
Right? So this equation for is actually equivalent, right, to the area equation without an epsilon, right? If x, right, for the equation of x divided by epsilon to the 2/3. And that's why the large x and the small epsilon limits are the same limit. And you see that here, if x scales like epsilon to the 2/3. Good. Yes. Okay. Are we okay? Good. So this is so now you see you don't have to work hard anymore. You have any equation with every q you want, provided that epsilon is small, you can calculate these simple two quantities and write immediately the asymptotic expression. That becomes better and better as epsilon becomes smaller and smaller. Okay? Good. Fine. Now we want to implement it. However, you see, the local analysis, what was, meanwhile, I just want to address your question, namely, why I'm not taking the what's happening if here I have minus x and not x? Because here I've taken plus minus of square root. So I mean, because I have s not squared is q. So I should take either x or minus x. The point is that if I'm taking minus x, right, then I will have here, I have the logarithm of minus 1 times x, which is the logarithm of minus 1 times plus the logarithm of x, right? What the logarithm of minus 1 will give me, it's I, right? And so, I since it's a linear equation, I can always absorb it in the coefficient, in the A here. I mean, it's a linear equation, so in any case, my equation is determined only up to a constant. So I can absorb every square root of minus 1, or the ln of the square root of minus 1, or whatever you want, into this constant.
But what to do if we change the sign?
This,
log 0 is not
no,
defined even
okay,
in
this is still a problem. You have asked two questions. This is one question. Right? Fine. Now, as you remember, the problem with the local analysis was that I have recovered what the function is doing at infinity, but I don't know what it is doing at 0 or what it is doing at minus 5. And my problem is that if I have boundary conditions, this is all what global analysis is about, right? Why we are interested in global analysis? Because we'd like to address global questions like solve an equation with boundary condition at 0 and 1. And this I cannot do with local analysis because I'm doing local analysis at 0, I have a constant, I'm doing local analysis at 1, I have another constant, I don't know how to match it, right? I have to interpolate between the two. So the WKB analysis provides us with a methodology that allows us to satisfy boundary value problem. Okay? How we are doing that? In a sense, the boundary value problem, the boundary layer technique that we discussed yesterday, is a technique in which we somehow separate the problem and allow us to do local analysis in a very small region where the epsilon term is important, right? Here it's sort of a different approach that we assume epsilon to 0 all over. Epsilon small, epsilon all over. Okay. So, okay, let's start with the most idiotic question. Oh, no, sorry. Let's start with general. To treat general is with Schrödinger equation. Here is the Schrödinger equation. Here is the Schrödinger equation, right? And I would like to just to replace this by epsilon squared, right? So this will be epsilon squared. So that's it. Write it here. So epsilon squared is h squared over 2m, and phi is y. But I don't know to switch notations. Okay. So what is the WKB approximation? This is Q. This is Q, right? And the WKB solution will be y is a times e to the integral up to x of the square root of v of x minus e, or v of t over v of x minus e to the power of 1/4, okay, plus b e to the minus the integral over the square root divided by the same thing.
Don't you need to 1 over epsilon?
Of course. Okay. This is the most general solution given the most general solution of the Schrödinger equation, and now we only have to satisfy the boundary conditions. Okay? Good. So let's solve the simplest problem on Earth, namely, not really simple, but I mean, it has its own difficulties, but namely infinite potential well of okay, this is L, and the potential is infinity outside and 0 inside, right? A particle in an infinite potential. Okay, so what is Y? V outside, okay, our boundary conditions are Y of 0 equals Y of L equals 0. That's the boundary conditions. Now, V of X is 0 inside the well, right? Inside the well, V of X is 0. And, okay, so what do I get?
Sine.
So Y is asymptotic to actually A times E to the 1 over epsilon times the integral over the square root of E, minus E. Okay, square root of minus E is I square root of E. Right, so I have here I square root of E times X, because the integral is over nothing, plus divided by what? By, again, E to the 1/4. I don't need the, again, it's minus E, but I don't care. I absorb the minus 1 to the 1/4 into the A. And then I have plus B E to the minus I over epsilon square root of E times X over E to the 1/4. Okay? So you know this is cosine and sine, and I have to satisfy the boundary conditions, so I will choose a sine, right? So Y is actually A times the sine of square root of E X over epsilon divided by E to the 1/4, right? It's not A now, it's B, whatever coefficient you want. And now this automatically satisfies that Y of 0 is 0, but it doesn't satisfy yet that Y of L is 0. To satisfy Y of L is 0, what I should do? I should require that the square root of E times L divided by epsilon is what?
N pi.
Is n pi, which means that E is n squared, pi squared, epsilon squared over L squared. And if we now remind ourselves what is epsilon squared is h bar squared over 2m, then we get h bar squared, pi squared, n squared over 2m L squared, and this is of course the spectrum of the particle in a potential, right? In an infinite potential way. Good. So note that we got the exact solution for every epsilon, even for epsilon equal 25. Right? This is an incident. It's not generic property. Generically, okay, we will speak in a moment. Any questions about that? No. Note that because v of x was 0 everywhere, there is no change in sign of q. Right? So I sort of hide under the carpet the problem of changing of a change in sign of q. And I will continue to hide it under the carpet in the next problem, but then we will dig it and start dealing with it. Okay. So the next problem we are going to deal with a generic. We are going to deal generically with any regular Sturm-Liouville problem. So what is a Sturm-Liouville problem? A Sturm-Liouville problem is a problem of the form y double prime is equal to or plus, wait a moment, plus y double prime plus e times q of x times y equals to 0 with the boundary condition say y of 0 equals 0 and y of pi equals 0. Just so you can choose any other number here, right? And the Sturm-Liouville problem is regular if q of x is larger or smaller, if q of x do not cross 0 between 0 and pi. So again, I'm continuing to avoid your problem. Okay? Now, so what's the relationship between Sturm-Liouville and this? Of course, it's the same damn thing because we can divide Sturm-Liouville by 1 over e, and we get this. So e is like 1 over epsilon squared, right?
Minus 1.
So small epsilon is like large e in Sturm-Liouville. Okay? Good. Now, as you may know, I guess you were taught that. Let me know if not. Every Sturm-Liouville equation have a complete set of eigenfunctions and eigenvalues, right? That satisfy the orthogonality relationships that integral from 0 to pi over of the x, q of x, yn of x, ym of x is equal to delta mn. Right? How do I prove that? Very simple. By construction, by definition, ym double prime plus em times q of x times ym is 0, because ym is the mth solution of the Sturm-Liouville problem, right? And now I will multiply it by yn. It's still 0, and I will integrate over everything between 0 and pi of all this equation. So and now, okay, I'm not going to touch that, but here I can do 2 integration by parts and move the derivative to this, right? While still, and there is no contribution from the end, from the boundary terms, because each of the y's is 0 on the boundary. Okay? So by the same token, I have satisfied that. Yep. And of course, this can be true. So now I can take the ym. Everything is multiplied by ym. Okay. And what is yn double prime?
EQ
E and
Y.
Yeah, so I can write that the integral from 0 to pi of ym ym times yn double prime is minus z, right? So I have ym, and here I have em minus en times times q of x times yn. This is 0. Right? And so there are two options. One of them is that em will be equal to n, in which case I have the delta, right? And one of them is when m is not equal to n, there is no other choice but that the integral with respect to the weight function q will be 0. Okay? So this is the characteristics of the Sturm-Liouville problem. Now, if I would like to solve, to find out what are the EM, what are the energies, and what are the eigenfunctions actually, then I can say, okay, so I'm writing y, what I'm going to do, yes, so I'm going to write what will be y. Y will be in WKB A divided by, remember, yes, the relationship that, what is our relationship? That epsilon squared is 1 over E. Right? So epsilon is 1 over square root of E.
It's minus.
No minus. Why?
Because here it's on the other side. Both terms are on the left side. Should have
Yes,
minus.
yes. Right. Okay. So epsilon is I over square root of S. Good. Thank you very much. So y is A times E to the I over square root of E. No, I times square root of E. Right?
The square root of ish is constant.
Square root of E is constant. So I have to.
Yeah, but it will cancel out that you will have minus.
I have E to the 1 over epsilon. What is 1 over epsilon? 1 over epsilon is minus I square root of E. This is 1 over epsilon times the integral up to x of q of t dt divided by, again, what I have is q to the 1 quarter. You see? Plus b times e to the plus I square root of e, integral up to x of q of t dt, divided by q to the 1. And again, these are sine and cosine. And if I want to satisfy the boundary conditions, I can write it as a divided by q to the 1 quarter, that I don't care about, sine of square root of e, integral up to x of q of t dt, integral from 0 to x. So when x is 0, this is 0, right? And now what I have to make sure? That when x is pi, this is n pi. So the quantization condition is square root of e times the integral from 0 to pi of q of t dt must be equal to n, right? N from 1, right? Because if n is 0, then I have 0 everywhere, right? And this implies that E is n squared pi squared divided by integral from 0 to pi of q of t en, right?
Sorry, it should be square root of q inside the integral.
That's square root.
Yes.
And square.
dt.
And you should put on the
All this square.
On the original y, it should be 2 square root of q.
What?
On the original y, it should be square root of q.
Sure. Yes. Okay. So once you just you see, so I want the eigenvalues and the eigenfunctions of this problem, which is equivalent again to Schrödinger equation, but you know it's a Schrödinger equation, but q of x is arbitrary, right? And you can, it's like having a, you know, infinite potential well, but now on the hill you have
small
whatever,
perturbation.
something like that, right? Whatever you like, and you want to find the energies. Here are the energies, and these are the wave functions. Of course, it will work only in the limit of small epsilon, which is now what is the limit of large energies, right? So it is not going to work. It is going to work here. For the large energies, we are going to get correct results. For energies that are close to the bottom of the potential well, we are not going to get the correct results.
It's called quasi-classical.
That's a quasi-classical approximation. Yes. Okay. Good. So, having done all these maneuvers, now we have to go to the real problem. Use. Okay? So the real problem is that everything we did explodes if q of x, somewhere in the region we are interested in, crosses 0. Because we have to divide, always divide by q to the 1/4, and this will blow up. Not good. Not good. Fine. So this is the main interesting story in WKB. What we are doing when q is crossing 0. But before, okay, yeah, okay.
What if q crosses 0 beyond the borders of our...
Wait. Before that, let's explain ourselves when q is going to cross 0 in a physical scenario, which means for Schrödinger equation. So you remind that for Schrödinger equation, what we have is epsilon squared y double prime, y is the phi, epsilon is h bar, blah, 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 equals to v of x minus e times y. This is q. When q crosses 0, what's the name of such a point?
Turning point.
Turning point. Thank you very much, right? Because you know what's happened. If I have, for example, a particle in a potential like that, right? This is a potential, v of x, and this is the energy. Yes? What our particle is going to do classically? Classically, here it has its total energy is above its potential energy, so the rest, this is the kinetic energy. And it will move, say, to here. Here the kinetic energy is 0, and it turns back and go to here, and so on and so forth. So the points in which E is equal to V and right, the points in which E is equal to V are the turning points. These are the turning points of the classical motion. Now a classical particle actually visits only the turning points. It cannot visit outside. However, to solve such a, usually in quantum physics we are solving such problem with the boundary condition y plus minus infinity is 0. Right? Like, you know, if you want Schrödinger equation for a harmonic oscillator. Okay? Which implies that now we have to know what is the solution here and here also. Okay, so we must find a way to cross the turning point. And we know that our analysis, that our WKB analysis fails at the turning point. Right, so here WKB fails. And we cannot make any connection between the expression here, where we can use WKB, and we can use WKB here, but if we want now to have the, you know, the constants of the, if you want to know what are the constants of integration in order to solve the boundary value problem, we do not have a way to do this. Right? So our main problem is how to overcome a turning point in the when using WKB. Right? Here I implemented it for the regular Sturm-Liouville, and I force it having no turning points in the way. Right? But once I have a turning point, I must implement another technique. So this is what we are going to do from now on. Look what happens when we have a turning point and we must overcome. So, what we are going to do. First of all, I would like to concentrate on the region here. So I am forgetting about this turning point. So we start with one turning point problem. And in order to make things more nicer, I will take this turning point to be 0. So if I'm plotting q of x as a function of x, okay, you see? Q is what? Is v minus e, right?
Yes.
So here in the region from here to here, q is smaller than 0, is negative, and here q is positive. That's why I'm going to get here, when q is negative, I have an I. Square root of q as an I, and I have a sine and cosine like function. And here I will have exponential decay or exponential growth, as usual. So I know how to solve things here, I know how to solve things here, and so for the moment I will plot now q of x as x, and I know that it crosses 0 here, it is above 0 here and below 0 here, so it will go like that. What?
Why does it cross 0 and x equal to 0?
I'm just defining this as 0.
Okay.
That's all. Good. So, I can say that if x is larger than 0, I will call it the blue regime. Right? In the blue regime, what can I say? I can say that y is what? Is a e to the minus 1 over epsilon square root of q square root or integral, sorry, over x square root of v minus e dx dt, right, divided by v minus e to the power of, okay, instead, do I want to, what do I want to do? Okay, I want to write v minus e as q. And here it's q to the 1 quarter. Okay? That's fine. Why I'm not taking the b to the plus? To satisfy the boundary condition.
Yes.
Right? Because this satisfies the boundary conditions at infinity. Okay? Good. This is why, let's call it region number 1. Now, here in this region, let's call it region number 2, I cannot use the WKB. Okay? What should I do?
Matching
With what?
with the inner quadrant.
No, but I should have an overlap region. No, for a boundary layers you need matching. For matching you need an overlap region. Now the question is, what I can do here? I cannot use WKB because I'm too close to 0. So I cannot jump from here to here. I have to find out what is y in region number 2. Here is the trick. In region number 2, I am saying that in region number 2, I claim that y epsilon squared y double prime is equal to ax y. Why that? Because it's a Taylor expansion. Exactly. I know that it's 0 is 0. So unless some gamad rasha make it x to the third or something, right? In the generic case, I will have x. This will be the behavior close to 0. Right? And what is this equation? Airy. I just want to, right? I just want to use also this, right? Right? In order to. So I can say that I will define z and x to the over gamma. What should I want? What I want to do? Yes. Again, okay, what I'm doing, let me just write something, a little something here, which is that, right, I'm saying that at region 2, q of x is ax plus bx squared plus cx cubed and so on and so forth, and I'm taking only the ax, assuming that I'm close enough to 0. So now I can define z as a times x divided by epsilon to the, what it was, 2/3. Right? And in terms of this z, you can check that y double prime with respect to z is simply xy. So I can use the solutions of the Airy function. Zy, yes. So I can use the solutions of the Airy function, just plug z instead of the x. Right? So the solution, so now I know that in the region number 2, y2 is what? Is Airy of z, meaning it's Airy of ax over epsilon to the 2/3. Now, why I'm not taking Bailey?
Because Bailey explodes.
Exactly, because Bailey will never match this garbage. It should go down, right? And Bailey is exploding. Okay, so in order to match these two, I have to, okay. So now I know this is Bailey and this is the solution, and now I can match. What will be the matching? The matching, in order to match this and that, I should take that at x over epsilon goes to infinity, or x over epsilon to the 2/3 actually goes to infinity, right? And match it with that when x goes to 0. You see, same trick that we did before. Now we are doing the matching. Note that it's more, what we are doing now is even more, the gymnastic is even more impressive, because we first did asymptotic analysis in 1 over epsilon, and now we are doing asymptotic analysis in x. So it's not it's a matching the matching, because right we are doing 2 steps of asymptotic analysis. But in any case, so what can I say about this function when x goes to 0? When x goes to 0, what I have is a e to the minus 1 over epsilon integral up to x of the square root of q. But we decide that q is ax plus bx squared, at plus bt squared dt. And for the moment, we neglect the bt squared term, right? Because x is small. And we have to divide this by, again, q to the 1/4, which is at plus bt squared to the power of 1/4. And again, I will
X.
neglect
Yes, but here
this.
it's
Not C, but
ax. Ax plus bx squared to the power of 1. Okay? Now, what will be the limit of this one when x over epsilon to the 2/3 is much larger than 1? I have to use the asymptotic of the area for large argument. And you know what it is.
yes.
Right?
Exponent.
The asymptotic of the area for large argument is what? Is e to the minus 2/3 times the argument to the power of 3/2. So I have a to the 3/2 times x to the 3/2 divided by epsilon, and now I have to divide it by the argument to the power of 1/4. So I have a to the 1/4 times x to the 1/4 divided by epsilon to the 1/6. Okay? Now, just one little comment. If you remember, we derived this with linear analysis, and in linear analysis of local analysis. And in local analysis, we don't have the prefactor, because the prefactor is just a constant that you have to define in order for area of 0 to be something, right? You have to decide what area of 0 is, okay? And the actual constant, if you look at the holy books, is 1 over 2 square root of pi. So we have here an extra constant, which is 1 over 2 square root of pi. Now, here is a question. We have this. Does it match to this?
Yes. You have A equal to epsilon 1 over 6 over the square root of pi.
Okay, I have okay, but okay, I will. I'm not using the blackboard or whiteboard in an appropriate manner here, but okay. So, what I will get from here is A. Now I have e to the minus 1 over epsilon times square root of A times the integral up over t, right? Which was square root of t, which is t to the 2/3, 2 to the 3/2. So I have here 2/3 x to the 3/2, and you see that the exponent here. Wait.
You also square root of A.
And I have the epsilon. Yes. So this and that is exactly the same. Unbelievable. You see? Now, in the denominator, we have A to the 1/4 times x to the 1/4. So what I should do in order to match this and that?
A is equal to epsilon to the minus 1 over A to the 1 over 6 over 2 square root of pi.
I will get A is equals to epsilon to the 1/6 over 2 square root of pi.
The exponent A.
Yeah, don't you missing one
I have a mistake here. Wait.
קטנה כאילו,
Yes, you've forgotten.
What I forgotten?
A.
little a in the exponent.
On the first time you got square root of A, and in the second one you get A to the 3/2.
Yes.
So you should have another A.
Wait. Okay. Sorry. Okay. I skipped a stage. I try to save time. So, okay. We had the actual equation we had was y double prime at region number 2. Y double prime times epsilon squared is equals to A times X times Y.
Yes.
Okay? And now we want to define Z such that, okay, Z is X over gamma. Okay? So I have epsilon squared divided by gamma squared y double prime with respect to Z, is equals to A times gamma times Z times Y divided by epsilon squared. Sorry. A times gamma times Z, Y. So y double prime is A times gamma cubed divided by epsilon squared times Z1. Right? So I want to find what is gamma. Gamma is epsilon to the 2/3. Okay? Divided by a to the 1/3. You see? And therefore, z is what? Z is x over gamma, which is x times a to the 1/3 divided by epsilon to the 2/3. So I have here, it's not a, this is not a, this is a to the 1/3. So here we have a to the 1/3, so this is a to the 1/2. And this is not a to the 1/4, it's a to the 1/12. And therefore, in order to match this and that, so the exponent matches perfectly. And here, what I need a divided by a to the 1/4 to be equal to 1/2 square root of pi a to 1/square root of pi epsilon to the 1/6 divided by a to the 1/12. Now, a to the 1/4 divided by a to the 1/12 is a to the 1/6. And therefore, a is equals to 1/2 square root of pi a times epsilon to the 1/6. Yes. I wanted to save time, and you see the result. Okay. So we know now what a no. I should have, of course, an arbitrary constant here. Let's call it D. Yes. These are the relationships between A and D. If I know A, then I know D. Now, note that what I did here was remember, this was Q and this was X, and Q as a function of X goes like that. Right? Now, we had the blue regime of Y1, and we have the black regime of Y2. Question: is there an overlap region? We did a matching, right?
We suppose so.
So it's supposed to have an overlap region. But is there an overlap region? So let's see. First of all, what was the assumption that allows us to go from here to here? We assume that X is much larger than epsilon to the 2/3. Right? So in the overlap region, X must be much larger than epsilon to the 2/3. Yes? And this allows us to expand Y2 for large argument of the area. Here, what I did is to neglect this term in the exponent. And if you remember, in order to have a asymptotic relationship, I want this term to be small. Absolutely small. Right? Now, what I have neglected here, so square root of AT plus BT squared is square root of AT times the square root of 1 plus b bt squared bt over a, right? And bt over a is small compared to 1 when t is small, right? So I can write it as a square root of at plus I have to expand the square root, right? To expand the square root, it's so I have b over 2a, say, times t. Sorry, 1 plus. All in all, I have a square root of at plus what? Plus b over 2 square root of a, which is a number of order 1, I don't care, times t to the 3/2. And this I will have to plug here and to integrate. You see? When I'm integrating it, I will get, right, after integration, this one gave me x to the 3/2. And this one gave me a contribution b over 2 square root of a times x to the 5/2 divided by 2/5 or something. Okay? So all in all, the extra term will be the extra term that I've neglected here, right? Give me something which is of order 1 over epsilon, this epsilon, right? Times x to the 5/2. So what I need in order for this term to be much smaller than 1,
X be much lesser than 2 epsilon to the 2 over 5.
yes. So I want x to be also much smaller than epsilon to the power of 2/5. Are these two conditions compatible? Why not? Is there a region in space that actually satisfies these two conditions? What?
Yes.
Yes.
Yes, why not?
Why? Why not? I mean,
No, because
because
epsilon is
2/5 is much smaller than 2
Yes, but
thirds.
epsilon is less than 1. Even
Yes.
much less than 1.
So when epsilon goes to 0, this will go to 0 much faster than that. And for that reason, you have x which is much smaller than that and still much larger than that. Right? As epsilon goes to 0, these two conditions are compatible. Right? So what I did is legal, right? And what I did is to establish a relationship between A and D. This is what we did. Established a relationship between A and D. Okay. Now, all this was done in order to, right? Here we have the area function, right? Here we have the a e to the minus integral of square root of q over epsilon. Here we have, this is y1. Here we have y2, which is area. D times area. Okay? Now, what will be here?
The I.
Exactly. So, but here I have both, I have two, okay. I have
You have sinus and cosinus.
sine and cos, oh, yes. So in general, what I will have here, can you tell me what I will have here? So let's call this region number 3. Region number 3. And in region number 3, I claim that y3 is asymptotic to, of course, I have here square root of minus q of x, sorry, minus q of x to the power of 1/4, Why I'm taking minus? Because q is negative. So I'm taking the minus and everything, all the i's are absorbed in the coefficient here, which I will call f. A, B, C, D, E, F, G. Okay? And what I will have here is exponent, but not exponent of the integral over the square root of q, but of I square root of minus q. So I can write it as sine, say, sine of 1 over epsilon integral up to x of square root of minus q dt plus some phase, an arbitrary phase, because this is the most general solution. Okay? And I have to match y3 to what?
Or the area.
To the asymptotics of the area at large negative argument. Okay? So what is the asymptotic of the area at large negative argument?
Also sine.
Wait a moment. Okay, the asymptotic of the area, of the same area, right, at large negative argument is d times square root of pi divided by square root of pi 1 over minus z to the power of 1/4 sine of 2/3 times minus z to the power of 3/2 plus pi over 4. Right? This is the asymptotic of this at large negative z. Okay? So I should compare this with that, where again I should take, for this I should plug this z and take x to be much larger than the absolute value of x to be much larger than 0, and for this I have to take I have to take x to be small. Okay? You see that. So okay, I will just end this part. Again, so if I'm taking this, first of all, clearly phi should be pi over 4. This is for free, right? So phi is pi over 4, and we take care of the rest, right? So here what I have is sine of 1 over epsilon times this integral, and this integral when x, so I have, this is this integral, so I have a to the 1/2 times what? Times x to the 3/2. Here is the absolute value of x divided by 2/3. Right? And all this is divided by minus q, which is again absolute value of x to the 1/4, and again I have a to the 1/4. What about this? This will give me d over square root of pi times 1 over, this is Z, right? And X is negative. So I have A, again I have A to the 1 over 12, absolute value of X to the 1/4, divide, and upstairs I have epsilon to the 1/6, and then I have sine of 2/3 times 3/2 times X to the 3/2 times A to the 1/2, because it's A to the 1/3 times to the power of 3/2, divided by epsilon to the power of 1 plus pi over 4. Good. So you can see that the argument is the same argument, the sign. There is a perfect agreement about the sign, and everything. We just have to make sure that this is equal to G. So we discovered that G is D divided by square root of pi times I have a G here, times epsilon times A to the power of 1/6 times D. Yes, that's it. That's it. So we have this, and we have that, and so now we know here our argument here here everything is proportional to D, okay, and here everything is proportional to A. So here we have D times the e to the integral q, the WKB thing, and q to the 1/4, and here we have A, and now we can write D. I'm sorry.
You mean you want to equate between A and G?
Yes.
To see the function
but this is not G. This is not G. This is D. I used D twice.
No, wait.
No, this is D.
okay.
This is D.
No, what?
No, this is
G.
okay. This is G. This is
That's
G.
right.
Fine. This is G.
Yeah. You
So
can-
I know I want to make connection between G and A. So I should plug D. For D, I should plug 2 pi A. Right. So this is equals to
You get that A is G over 2.
2 pi, 2 square root of pi A divided by epsilon A to the power of 1/6. This is D. And now I should divide it by square root of pi and multiply by epsilon A to the 1/6. So the epsilon goes away. I owe you 5 minutes. And the square root of pi goes away. And at the end of the day, we see that G is equal to 2A. That's it. Right? So this is how we cross the Rubicon from side to side, right? And make a connection between the WKB solution here and the WKB solution here. Okay? And so, unfortunately, if I had extra 20 minutes, I would end up show you the grand finale, but because I do not have this time, we will show it next lecture. Thank you very much. עשיתי טרנינג פוינט אחד, ובפעם הבאה אני אעשה 2.
אוקיי.
אוקיי, ותודתנו תודתנו לאיש שתרגל אתכם כל התקופה הזאת, החל משבוע הבא הוא מתגייס ואני אתרגל אתכם for what it worth. אז שבוע הבא תתכוננו כי זה 4 שעות. להתראות.
So we did not show you a specific example of calculating the energies and all of those stuff.
We did one example of a particle in a box.
Yes.
Okay, very good. So
Yes.
the first thing I will show you how every second order equation is actually Schrödinger equation. He did that, the whole development of that. I think I mentioned that in the tutorial of ISP, that you can actually reduce any second order differential equation to the form of y2 dots equal to. That is why. That is. I had intuition on that. For that reason, there is no any other reason for it. And he showed you what happened near a turning point that is actually a function and all of those stuff. Okay, very good. Very good, very good. That's good. So most of I will be able to. Don't remember. Okay, I have it here. So I will be able to just jump from stuff to stuff at the start. So you saw to write all equations as the form of if y2 primes plus a of x, y prime plus b of x, okay, times y equal to 0. How do we find? We want to do some transformation to y to w, and y and w will have the form of y2 prime equal to qx w. That you do by assuming that y is u of x times w of x, plug it into the equation, and take to 0 the factor of w prime. You did that with Schnurb.
You did
Right.
it with an exponent, but it's the same. It just revealed that u is gonna be exponent.
Okay, yeah. So let's just do it quick. So it's very quick. Let's do it quick. So I will have the formula here. So it's a little bit. So now, second derivative. Plus w of x and plus u of x. Now just plug it in. That's what we will do. And now just take in all the factor of w tag 1, the first derivative of w, okay, from plug it in. From that we don't get anything. From that we get one thing, which is ax ux. So let's write that, ax ux. We just write in the coefficients of y of w prime, right? And from that, the 2 prime, we just get in 2u tag of x, and we want it to equal to 0 and find the u that satisfies that equation, and that will give us equation in that form, which I will write after that what is q. U is actually it's just separating of variables, Now just integrating, dividing by 2, and that we get that u of x. We don't care about any coefficient here, right? Why? That is linear OD, and that coefficient is equivalent just multiplying it by some coefficients, so we can suck it into the W. So what we get is e minus integral of x from any point you choose of a of x divided by 2. That is the equation. And what is q? What is q? Now we just need the coefficient of w. Okay, from that we don't get anything. From that we get one thing, which is u prime of x, right? And that is times a of x. And from here, what we get, we have just u of x times b of x plus u of x. So what it is actually is just minus a of x squared divided by 2 plus a of x b of x. Everything here is times u, which is just integral to x of f(x) divided by 2 dx. Right? That you saw already in lecture. Just want to write the equations here, and that is exactly the solution you got in lecture, right? So it's good. So let's do one example. What is your favorite ODE? Schrödinger.
H bar.
Which is not Schrödinger.
G.
I would expect you guys to say something like that. Vfx dot plus omega squared x, harmonic oscillator. So that is completely solvable, but just for no reason do it. For sport, if you like. If you like, you can always. By the way, you can always do perturbation theory and then do perturb solution to the perturbation. Like if you don't have if we will have something like gamma x to the 4 extra here, you can find the solution when gamma is very small and write the solution. You need some asymptotics here, right? Or find zero order and approximate it around it, and then you get the solution. But let's just do it for that case. So first thing first, what is u of x for our case?
A is just cross.
Wait a second. Wait, did I miss something? No, I'm okay. Okay.
B squared.
W of x. Right? Yeah, I were missing that thing. No one corrects me.
Because you believe.
That is bad thing.
No, I don't believe you.
Don't ever believe the tutor.
But here I do believe you. So.
Don't ever believe the tutor. You can say a lot of bullshit.
We know.
So now just write in u to prime of x. Okay. So what is u of t? We have first thing first, write in it in appropriate form as that thing. And now, what is u of t? In that case,
e to the minus half of b.
let's do it from 0 to t of what? A divided by 2, b divided by m dt. Yay, what we got is bmt. Nice, that's what we got. Now just writing now our w, 2 dots,
Divided by 2. Bm divided by 2.
right. Now w 2 dots is what is our q? Okay, our a is, let's use that equation actually. So 2 primes, what we will get is b squared over 4m squared. The next term will be b divided by 2m times b divided by m. The next term will be omega squared divided by m times u of x, which just come out of the equation. Then we get that thing, right? E to the minus b over 2m b equal to w t. That's it. Yes. Oh, I have that term which I took it already. Okay, I think it's right. So everything here is adding up to. Are you with me? That is just adding up to 3 b squared divided by 2, 4 m squared plus omega squared divided by m. Okay. I'm what?
Just a constant.
Yeah. Times e to the minus b to m. Yeah, I'm just surprised that they survived, but I guess it makes sense. No, they is not surviving because what I have to do there is actually divide everything by u of x. You missed that also. That is just why I have to divide it, because from y to primes we get coefficient of u of x. We have to divide the whole thing, and actually that means that also, no, the solution here is fine. The equation is supposed to be divided by u of x, but it doesn't affect on it, and therefore that's that. And we left with that thing, which now actually it's solvable. We know, everyone knows how to solve that, right? That is easy equation, but you can use WKB. I will not use because it's too simple. Just
And then when you find the
I'm not sure, by the way, about my calculation. So, but you got the idea.
But
Probably
we need to assume that this coefficient is sufficiently small, right? In order to use
That coefficient is what?
is large.
I didn't use here
Should be
still
small if it's,
WKB, but
Yes. Very good.
Yes.
but
It's
if
opposite
that's
and, in
if
this
you're
case,
worried,
it should be
you can always
large,
define
yeah.
you can always define here epsilon squared if that satisfies you, right? WKB is with epsilon squared. I'm not wrong.
Yes, and now it's absorbed into Q.
When epsilon is equal to 1 for taking the limit for what you need. We practically did it all the course sometimes. Every time in the course we just introduce epsilon equal to 1. You need to verify.
Yes, but
I think
if you
it's
plug
should
epsilon
be
equals
M.
to 1, it won't be satisfied by the UKB.
Wait, I think it should be with a minus the minus b in the start. Minus b squared over 4m squared. Not with plus.
Makes
And then you
minus, that is minus.
no, actually the other way around.
The other way?
Yeah, because you have minus b m.
No, that is with the minus. Yes. That is with the minus, because here I have just one term. You're right, but wrong on the minuses, and yes, I agree. Right? So let's do something more advanced. There's nothing advanced, that is last year tutorials, and the year before that, and the year before that, since Corona. So I can promise you there is nothing advanced there. My oscillator did. Okay. So in Schrödinger equation, the form of the equation usually is epsilon squared times q of x. And in Schrödinger equation, for example, q of x usually defined as the difference between the potential and the energy, right?
The other way. Since A is on the right
Yes,
side.
you're right. And what is epsilon in the case of Schrödinger equation?
Epsilon squared is h bar squared over 2.
H bar squared divided by 2n.
But h bar
Right.
is 1. Because we are physicists.
Right. Yeah, h bar is 1, and because we're dealing with large scale object without the Schrödinger equation, right? That is always verified.
Planets, stars.
M is very, very big. Has
H
to
bar
be
is
like that.
1. H bar is 1 in what universe?
In physics.
You're a theoretician? Yeah, it's a magician. And you're a
Naturally,
theorist or
H bar equal to C equal to
you're a theorist or experimentalist? If you're a theorist,
Yes.
you should stay. If you're an experimentalist, that is not allowed, and you should not be here because it's course for theories. Okay, there are experimentalists that take it because it's supposed to be easy. The test is easy usually. Usually. There are,
Take the course.
what?
I thought you were saying that there are experiments work with H bar equal to 1 is equal to
No.
No,
Okay, there are actually
you're
there
talking
are
about
there are
course.
experimentalists that do that because they just want proportional or things that distribute the same with the same behavior. Like they want to show that this experiment showed something that behaves exponentially. So they don't care about h bar, so they can set it to 1. Right? That is just statistics. What they will do is practically do everything with log scale and then show that the derivative or it's going linear just. So they don't care about what is h bar, they just want to catch the behavior. So there are experimentalists that will accept it, but let's stick now with our h bar. And let's see. So, and what we usually do in order to solve that equation is assume y2 prime is in the form of epsilon n minus 1 from n equal to 0 as n infinity, right? You start from 1 over epsilon and continue from there.
Y double prime or Y?
What?
Y. It's Y, not Y double prime.
Yeah. Accidentally wrote it like that. And did you wrote the next correction? I mean, the correction for S. There is S1. Let's see.
You mean S2?
S2. Yes.
He just said, he just wrote the equation for it.
Equation.
He
Yeah.
didn't
Yeah.
write
We
it
didn't solve
formally
it.
because he said epsilon goes to 0, so this term must go to 0 by construction.
Yes. What I'm asking is, if I'm asking if you wrote S2. If not,
no,
we will
Just
just.
equation for.
He wrote the equation for it, but didn't write it formally in terms of Q.
Okay.
We just said that we found S0, S1, and
Okay.
this
So
equation for S2 and S.
let's do it.
Have fun if you want to do
That is the next question. It's pretty dumb if you ask me, but okay. Let's do it. Just next order correction to WKB. If you remember, when we talked about ISP, I said exactly equation that in that form, and I told you what is S0 and S1, and I actually told you that sometimes there is small coefficient epsilon there. That's it. And you should remember what is S0 and S1 for the test. But each time you need to use that. If you don't have time, okay, say it in the lecture and the tutorial, we saw that. But usually, from what I saw in Nadav's test, he expects you to know how to derive it. That is the only thing that he expects you to derive in the test usually. But that is very simple. You just need to explain why you assume that in that form, why you start from 1 over epsilon, because you want to catch the divergent behavior, right, of the equation, and do all of the stuff with width and those stuff, and say, okay, the width is delta here. You set it with delta, start with 1 over delta, S0 plus S1 plus ta 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 ta, and find delta, which will be in the same order of epsilon, subset delta to
He didn't
epsilon.
write it on the lecture. He just
Okay,
said-
that is sad. That
he
is
just
sad, but
said this
okay.
is the solution, trust me. And we do trust him.
Yeah, but you can see that if I will just write it
Yes, you
with
can
delta,
just write-
it's divided by delta squared, then you say, okay, from balancing delta, that is the width, and now just take in that. Because what you want to do is finding the width, that is practically what you will do if you will do inner solution, right? And that gives you the full expansion. Like if you saw yesterday, you take more and more perturbation, usually because of the inner solution, not because of the outer solution. There is sometimes that, like we saw, that the outer solution suggests power series of epsilon, but the inner solution is power series of n divided by 2, or more terrible, more horrible than that, can be power series with epsilon ln, like we saw yesterday, which is pretty horrifying, and it's usually determined by the inner solution. So that is why it's some sort of boundary layers, because you find the width as you like to do if you will solve it with boundary layers, and now you just fully expand and do actually a method that is similar to ISP in order to find the solution.
What is
Irregular singular point. What
Just
you
that symptotic
did in
effect.
order to find the solution only in one point. But now, because we introduce a scale into the equation, you can, when things getting smaller and smaller, formally you can equate the coefficient of those epsilon to 0. You need to do it by induction actually, formally, but we don't care. Okay, we assume you know how to do induction already. You finish undergrad studies. You can just equate the coefficient to 0. So, okay, what we will now do is finding things until S2. And if you remember, you said that S2 is horrible equation. It looks really bad. And now I will prove it looks really bad by suffering and torturing myself to do it. So let's start from doing it. S0 divided by epsilon plus S1 plus epsilon S2 equal to y prime equal to S prime 0 divided by epsilon S1 prime plus epsilon S2 prime that's right, just y y2 prime. Whew. Now it's starting to get very tedious. Luckily I don't have to give you the homework on it.
Why not?
Because you want me to upload day after day homework?
Of course not.
Right. So Nadav will upload to you homework that he will make and do next week.
I'm not sure if it's better for us or not.
I'm also not sure. I never saw his homework, but if you will recycle homeworks, you're pretty safe, because the years before, 1 year before, it cannot recycle from Kessler's year, so it's lucky for you because we had horrible homeworks. But the year before that had really nice and easy homeworks that will teach you nothing and you can practically finish them in half an hour.
Sounds good.
So maybe we'll recycle them because that's where the last time he taught the course. So I don't know. Good is depending on what is your purpose, right? So now just equating that thing with, we need to multiply everything here by epsilon squared, right? With q of x times y, right? And very nicely we can just open this thing up. S0 times epsilon 0 plus 1 prime squared plus. I hope you had fun with seeing me doing those stuff, because for me it's torture.
Yeah, then you are working out on something that it's not really useful, so it's the best preparation for army you can have.
Right. It is useful because that is sometimes that is the catchy question in test, to just do it to third, second order. So we're just doing tedious stuff, but it's actually, it will take you hours from the test, but it's easy and you get 3 points pretty much. And that is sometimes the whole catch of the test if Schnell want to be nice. So it is something that is appearing. So it's useful if your purpose is getting good grade. But, and actually, like we saw yesterday with boundary layers, sometimes when you go to higher orders, you get different behaviors and really interesting stuff. So it's actually very interesting. And I think there is someone in the internet that wrote until the 6th order, but they get exponentially long. The 6th order is something like 30 pages. So he gives you mathematical code that you can just plug in and get your solution if you want to see it. Usually it's very nasty and you will not like it and will not be able to get any intuition from that. So usually you just tailor expand it around a specific point, and from doing global analysis you do local analysis, so it's losing the point of WKB, but I guess nice. It is nice sometimes, but I don't know. S2 prime. Whew. That is horrible. Last time I did it for last year, and I forgot how horrible it can be. Yes, I think I done a mistake here. Now just write in epsilon to 0th order. Is there something that is epsilon to 0th order?
Yes, S0.
Yes, that. S0 prime squared equal to Q of x. That is actually, now I will give you intuition on ISP, the regular singular point. Usually what you did in WKB is also good for what? For higher order stuff. So you can always introduce that epsilon and do that, and that will probably give you the right answer of what to just throw away. There is specific cases which is not the case, but usually that's what you do. Why? You just take in the highest order first derivative that you will have in when you substitute e to the s. So even if it's y3 prime, you will have something like that equal to q of x. Now taking the third root with respect to all roots, you will have 3 roots, so that means from 0th order you have all the solution. And it's usually the case. Only if something is very degenerate and some of the roots are degenerate for first order. That is the only case. So it's very nice. Actually, maybe after that we will do the same idea of WKB for y3 primes, just S0 and S1. Not more than that. I don't want to suffer and torture myself more than what I'm torturing myself already. But okay, so now epsilon to 0th power is just that. Now S0 tag is plus minus q of x, plus minus. Okay. Now S0 is just the integral of plus minus q of x dx, and epsilon 1. Okay, so from here, what is epsilon to the 1? We need everything that is divided by epsilon once.
S0
So
plus.
let's see.
Yeah, S0.
The second prime, right?
Second prime S0.
S0 second prime. Now the next thing is S1 is not, no.
2
That is
S0.
S0.
2 S0 prime, S1 prime.
Right.
Double by 2. You have 2 there.
Where?
2 on the other.
2 there on the S0.
Right.
Second.
Yes. And that is usually what you get, right? When you do ISP. So it's very, very nice to have those similarities. When now solving for S1, what we will get. So actually, just in most tests, you just have to do this thing again.
S0 prime. Not S0.
Yes. This thing again, and it's pretty much giving you 3 points. Right? Don't think someone will not agree with with what I said right now, which that is practically 3 points. And now S prime of that will be Q squared, 2 here, and Q prime here.
Q
Right.
squared, just Q, not square.
And I think is that
And this is 4.
4? Yes.
4 and Q, because you have, because S0 is
Wait
just
a
square
second.
root.
Yes, I agree with you. And now it makes sense because now S1 is what we all remember. I wish that we all remember. By the way, why don't take the constant coefficients? Again, it came from linear equations. Okay, so taking a constant coefficient will not give you a lot. It will be S1 plus constant, which is just like from our assumption that y is e to the s, plus c is like multiplying it by a. It's linear equation, it's one of the properties, right? So constants, we don't care about it. We just want to find 2 solutions, so for example we will be able to approximate the non-homogeneous term, if there is, with WKB. Nice trick. Right. Variation of parameters, I'm sorry. The non-homogeneous solution. So now what we get is minus
1/4 ln of Q.
Q. So our solution for now looks something like that. 1/4 root of Q e to the minus plus integral to x of square root of Q dx. That's it. Now the last equation, which will be blah, but we will do that, sadly enough. So now we have S, now epsilon to the 2nd power. Now S1, what is it? S1 squared. And now we have that thing, which will be plus 2S0 S2 prime.
Plus S1 prime 2.
Plus what?
S1 double prime.
S1
Double prime.
double prime, where is it? I agree with you, but where I wrote it? Right here. S1 double prime equal to 0. Therefore, just from writing that equation, you can already say why it's the. What? Now again, S2 equal to minus S1 prime squared plus S1 2 prime divided by S0. Oh, and there is 2 also because of that. So let's just, I will erase this thing because it's not helping me anymore. And I don't want to. I see that no one is writing, so it doesn't matter. So it's actually very easy, right? Very tedious, very easy. And now just writing it like that, minus S1 prime squared, S1 prime, 2 prime, divided by S0 is that thing. So 2S0 will give us the minus plus, good morning, minus plus because there is already minus, so and in the numerator there will be 0 to x, 0 to x, square root of q, right? Square root of q, let's see, dt, yeah, dt, and now, whew, no, that is very good. Now S1 will be q dot 16 in that form, and now the next derivative, that will be, oh gosh, yeah, that's why I say that it's get worse and worse. Just think about finding out S3. It's tedious, but I mean it will be, if you're doing it slowly and careful, 1 hour from your test, and it's 3 points WKB. If you want to calculate correction to frequency at some physical problem, for example, usually you will have to find S2, and therefore you will have to do that development. And if he asks you to find the even next correction, you will have to do it, I think, no, to S3, and you will find the next correction. That is one way. Usually, it's depending on the question. So now, q prime 1 minus q, okay, q of what is that? Yes, I think I'm right. That is the next prime of that thing. Okay, good. Now simplifying it. Yes? Let's just check in my notes. Not mine, actually. No one corrected me. That has to be a S0 tag. Now I cannot show you from where, but that is practically came from the. There is not such a thing in the multiplication which don't have tag, right? And that
so
is unit error. Just think about unit.
It's just q.
Yeah,
Just
it's so it is just q, square root of q. So with the plus minus still is here, still here, right? And now I will just do a shortcut, and I will see what has been calculated here, and will give you the final result, which is okay. That is S2 prime. You still have to remember that you need to integrate that, right? No?
Okay.
You're not happy with that?
No, I'm not happy.
I don't happy with that also. But you can see that if, for example, think about Q, which is negative, for example, you will get more and more corrections. But you want corrections in correction in phase, for example, that you will actually get from here. Because the first one, when you're just writing it, it's getting down here. So you will have correction in phase, but something stationary, right? That is the name. It will be just a small phase, constant phase, that will fix it, but not fix it to a specific point, but not actually do something. So, okay. What we will do now? Let's do that one. Yes? Okay. So now we have this stuff. Let's solve the real problem for a potential that you will choose. I don't care. What is the rule for Sturm-Liouville problem?
What do you mean by
Hmm?
what do you mean by rule of what?
What needs to be satisfied for Sturm-Liouville problem? Don't give me the. Okay.
You read my emission operator and the boundary.
Exactly. That's what I look for. The boundary layers should be 0 at the boundaries. Right. Exactly. So let's now doing some nice examples. So we'll see what is the example I prepared. So for example, let's look on Schrödinger equation, which will be in the form Liouville problem, which will be in the form of eigenvalues, that is in that form, with weight q of x, right? And what here will be e, epsilon.
Minus,
Yeah, 1 over square root of e. What that mean? We do it practically for large energies.
Yes.
So it's estimation that if you will take more and more terms, you can assume that the energy is smaller and smaller, but we don't have a better way to approximate it for now. You can do local analysis like I gave you and assume it's global and solve it with Schrödinger equation. So one option is do it for anything, taking a singular point, do some stuff around it, taking that point, solve it, assume it's valid for larger area or something like that, and then what you did in homework 3, I think, is practically you got the energies. Now we're doing global analysis, but we find estimation that works only for large eigenvalues, right? Yes? So we always suffer from something, but that is what the course is about. Just approximating with different methods, and when you will go to your research, you will need to know what is the correct method to use. Your case. Okay, so let's continue. And just for showing what happened here, let's add minus here. Is it affects anything? Yes. Just make it easier for me for getting quantization. That is the only reason I did it. Okay. So let's write right now a general solution to that. What it will be? We already have the form. Let's go to order to S1. How that called? That is the name. Geometry approximation and optical, right? You didn't talk about it? You heard about that? Okay. in tests usually I write geometry approximation or optical approximation. I don't remember which one is the 0th order and which one is the 1st order. It's called
Optical approximation is the 0 order. That I know.
So the geometrical is the 1st order. We'll see when you start to solving tests that is appearing a lot. If that's context. Okay, so will be 1 over 4th root of minus q of x e to the minus plus integration. We have here I, we have here q, d, t, t, right? And now, assume we have quantization for, let's say, between y of 0 and y of L.
Forgot the constants in the exponent.
I forgot the constants in the exponent.
In terms of epsilon. Should have, I think they should have I.
Yeah, here divide by epsilon, and here you have some, you're right. I substituted for epsilon equal to 1, but here I should take it.
And you should also have 1 if it's a minus.
Will be square root of it, and in here it will give me a power. Wait a second. S1, no, S1 is fine. I got now I think I'm fine.
You just need the I thing because
I
it's a
have.
minus. Oh,
I have already. I just took out the minus sign
yeah,
in
just
the root.
the plus minus.
Yeah, but you're right about the energy. Now just write in the boundaries. And now we got what we want. So the first thing that we will want is to write that with cosine and sine, because we can switch, it's practically switching bases, right? You know why it's switching bases? Okay? So let's write it with cosine and sine, because now we cannot satisfy that condition with only one mode, and we would like to satisfy it with only one. We will have to do it with plus and minus, right? And when we write it, let's write it in general form. We will get a cosine of 0 to x square root of q of t divided by e dt. That thing you did in lecture, right? You were supposed to do that, at least. B sinus of, let's write, square root of q of t divided by e dt. And now for our boundary conditions, because we're interested in we want to solve the Sturm-Liouville problem. What will be a?
0.
0, exactly. A will be 0 from x equals 0. We get a 0 from x equal L. What we get? We get equation on sinus, which is 0 to x square root of q of t divided by e that thing you did with Nadav, right?
Yes, we did it for potential
For specific potential?
potential well.
Potential well only when you have a barrier? What do you mean by well?
Potential well, you have zero potential
Box with
inside
infinite,
the well, and on the boundaries you
Infinite?
the function is zero because the potential is infinity.
Yeah, okay.
Potential
Wall.
well,
well,
called well.
the air,
Well?
Yes.
W-E-L-L?
the air, be free.
How enable?
More potential.
Oh,
potential.
okay.
As well,
Yeah. Okay, but that is more general, right?
yes.
I just assume here that the eigenvalue is very big. And we get approximation. That is practically the same thing, but with a little bit different case, right? So that is 1 over E. Then we get its time square root of Q of t dt, and that thing equal to pi n. And there you go. That is the first approximation of the energies. By dividing it and square everything, we get that E of n, the nth level, is approximately pi squared n squared divided by 0 to L square root of Q of t dt, everything here squared. Usually it's in quantum mechanics too. Is this here Ellie taught you WKB?
Not yet.
No? Okay, maybe later. But it's actually very nice, very nice thing. I'm calling it energy level, but I'm meaning actually eigenvalue. You actually got quantization, what you will expect. So it's very nice. And now let's play with it with just one function. Yes, let's do it for one case in Schrödinger equation, just to get the feel of it. So let's do something cool. Don't know if it will be solvable, but if not, I will ask you to open integral calculator. I did not prepare it before, but it's fine. Give me a potential for Schrödinger equation. Whatever you like.
1 over x.
1 over x. That we know the solution. Do you want me to do 1 over x?
1 over x squared.
1 over x squared. Okay.
1 over log of x.
1 over log of x. I will suffer from doing the integral of that
That is
thing.
why suppose
Yeah, I guess. Do we know how to do that integral? Okay. Let's do something.
just log it.
Log x. Okay, that is still not. Yeah, that is still not nice to get in test in quantum mechanics. But now let's start and develop our intuition on something like that. We can graph it and see what we're expecting it. So actually, we should have here even a turning point, right? In that potential, we will get energy and that thing, but for now we are not considering anything with turning points. That's supposed to be next tutorial. I will tell Snell to cover it, because I did not prepare it. So let's just look what is the energy level in that potential. We know it's bounded from one side, and from the other side it is not well defined at 0, right? So maybe let's do something with that, because now it will be in that form. Maybe that is more interesting, in my opinion. I don't know.
Wait, why x plan x is 0 is 0 at x?
At x equals 0?
Yeah.
That blows up to infinity as ln x, that go to 0 as x, that wins. That is linear, that is logarithm. Just use L'Hopital. Okay, so I think that will be even cooler. And
You're the one who need to solve it,
so let's start with the fun. What is the first step? Minus h bar squared divided by 2m y, wait, that is e times y.
What are you trying to calculate now?
Just writing the function.
Yeah, but what is the goal? What do you want to calculate now?
What do I want to calculate? Just the energy levels for that specific case. So let's do it like that, and we have x ln x. Oh, units is killing me. So there is no units here. Okay. Find yourself how to make that make sense with the right units and all of the stuff.
H bar equals 1.
What?
H bar equals 1. Everything is okay.
No, you need actually h bar to equal to square root of m.
M is 1.
Yeah, of 2m. What?
M is 1 also. Or 1.
Yeah, everything is 1.
But everything
Yeah,
you
yeah.
want.
For me, everything. M is half, so it will cancel out the.
Exactly.
Okay, so now just writing it with the form, with that form, x ln of x, y. I will assume there is epsilon here, right? We're supposed to have here some epsilon, which we don't have actually.
Wait, epsilon is 1 over square root of e.
Okay, we can do that, but we can. Okay, I agree with you. We can do it like that.
It is just how we define
Yeah.
all the parameters of this equation.
We don't really care, but yeah. So we will have to do a little bit different development of that, right? Because here we assume something that is different. I agree. And now we just have the solution that we had before, just plug it in. But now we need to be more careful with it. That is our Q of x. And let's see what were the equation. That were our equation, but now our Q of x is, our Q is also depending on E. And we get from our quantization, E of n, 1 over E of n, 0 to L. And now, I think that is fine. X ln x divided by En. I should write it with T. Oh, that is horrible. What did I do? That is bad.
You chose it.
That is as bad as possible. But I will do approximations because we already assumed that it's very big, and we took it to order the correction. Okay, that thing should be very big. E is very big, so that is very small, right? So we can do approximation of that to solve to order of epsilon. That is actually one order more than what we actually need. You can see that taking zeroth order, it's just one, so it's just L. Divide it and do the power, take, English is out. And now just divide it by L and taking the reciprocal and square both sides, we'll get actually what you will get for free particle, which makes sense, right? And now just taking the correction for our case, which will be E of n times L minus half. That's why I like the integral section, which we practically skip in this semester. T to ln T dt. Yes, I think that is right. I of n. And now it's just a matter of solving equation for E, which is supposed to give you, when you throw out the negative solution, is two possibilities, which I guess comes from symmetry, that one you will need to throw away because T has to be bigger than 0 for that thing. You can look on that as V of R, if that makes more sense, because it's in different coordinates. You can think about that. So that is abandoned small negative values of x. Do you see what I mean?
Yeah, but it's like, okay, if it's like x equal to 1, so the Laplacian you should.
Again, what?
If you take x to be r, then you should.
Yeah,
by r squared.
yeah. I should convert it to Laplacian, and I will get a horrible equation. But actually, it's very cool to use WKB in the radial form and estimate those stuff. I actually think we had that in homework when I did the course, and we got also in parabolic coordinates, and we were like, no. I think only Kalinsky suffered. We finished, by the way. There is just need to solve for E, and that's it. Everyone knows how to solve here from 2E. Right? Good answer. Fair enough. You just multiply by square root of E, pi n, square root of En. Actually, more than that. By En, you multiply everything. Now you have that thing, L times square root of En minus half some integral, let's call it I. Let's just write the solution to that, and then moving things to one side, Fn minus L divided by pi n square root. Let's square it.
No, but just.
Okay. Just now you can call that L. That will be L squared. Use the roots formula and finish. Yeah. How with time? I think fine. And finish. Yes.
Thank you very much.
It were 55 minutes, I think.
No, it was 1 hour and 10 minutes. Because we started with
Yeah.
50 minutes.
An hour.
Yeah.
But started half an hour earlier. No,
15 minutes.
15 minutes.
Yeah, it's fine. It's fine. I think it's not that hard of. It's not that hard.
טוב, ככה היה.
No.
טוב, תרגול. בחוץ יהיה קר. מה זה רגיש לפה?
נחמד סך הכל, לא? זה כאילו זה נושא חמוד, נחמד. פעם אחת בקורס מספיק שזה התרגול האחרון. פעם אחת הייתי צריך לעשות משוואת שרדינגר.
לא הייתה לך ברירה.
למה לא
I'm not
אוהב...
able to escape Schrödinger equation this time. This time it's all about Schrödinger.
אתה לא אוהב להשתמש בשרדינגר, אני מבין.
I don't like Schrödinger equation, I don't like quantum mechanics. I prefer it